Good morning, dear students. I start with complex number part 5. In this section, in this particular part, we would work out problems. And to your information, I'm starting with very general problems. My aim is ultimately that you start liking this particular topic. A very important topic, I have told you several times. Certainly, lot of problems there in your different competitive exams and in your exams, terminal as well as final examination. So first, you start liking your subject topic, complex numbers, and then after working this out, you start enjoying it. You start working more problems. And once you start liking and then enjoying, then you relish your subject. So that is why I started with gentle problems. All of you need to work, practice them. If a problem you are able to understand, try to do it by yourself. If a step is not clear, get it clear and try to work that out 2 to 3 times so that things become very simple for you. Now, our problem number 4 of this part, first problem of part 5, continuation of part 4, problem number 4. Find square root of two problems I have written. I'll start with the first and then the second. A square plus 1 by a square plus 4i into a plus 1 by a plus 2. My aim for this particular problem is I have to first express the given expression as in a square form. If I can express it in square form, then easily I can find its square root. Square form means I have to express both of them in a plus ib whole square form. This particular given expression has to be expressed in this particular form. If I can do that, from here I would conclude that square root of this number is plus minus a plus ib. So our aim is to express this or any problem on square root is to express in a plus ib form. To do that, in this particular expansion, there are three terms. One is a square, this is the basic of what exactly we need to do. This expression, if open, it is of this particular form. This is the real part and this is the imaginary part. So therefore, this particular given problem has to be expressed in this particular form. If I can do that, then automatically I will return back to this and that would be my required answer. I start with the given expression a square plus 1 by a square plus 2 into 2i into a plus 1 by a plus 2. That means I have written this into 2ab form, this particular form. And on further simplification, I find that this portion is A or B and this is A or B. So therefore, if I write this as A plus 1 by A whole square minus 2 minus 2 minus 2 plus 2 into 2i into A plus 1 by A plus 2. Sorry, this problem is actually minus out here. Minus. So this is also minus. Therefore, A plus 1 by A whole square plus 2 into 2i into A plus 1 by A minus 4, which is equal to A plus 1 by A plus 2 into 2i into A plus 1 by A plus 2i whole square. When your concept is clear, when you know what you need to do, that you need to express in this particular form. So therefore, you have now expressed A square, B square, and this is the rest to AB form, which may be further written as A plus 1 by A plus 2i whole square. Use your brackets. We generally work with first and the third bracket. You may even use second bracket. No problem with that. So just see, the given expression has been now expressed as A plus IB. I repeat once again, this is the given expression. I have to express in this particular form. Why I have to do that is the reason is that if I can express in this particular form, directly I can write the square root as plus minus A plus IB. So therefore, I have to reduce on my simplification. This is also minus, mind you. Minus, 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 which is 4i square, that is minus 4, required square root of the above expression is plus minus A 1 by A plus 2i. Practice. And now the second part of the to find the square root. Now our given expression is 1 plus I A square minus 1 into root over A square plus 1. Again applying that I have to express this in square form, in A plus IB form. If I can do that, I can easily express this as a square root and I can find my value. But I observe this is the 2A IB form. 2 is missing. I multiply first 1 by 2 to numerator and to the denominator. My expression now reduces to, it is just arranging and rearranging. First, you locate the 2 IB form, 2 IAB form, and try to locate what is A and what is B. Further, I can write this as half into A square plus 1 a square plus 1 plus minus a square minus 1 plus 2i root a square minus 1 a square plus 1 bracket closed. On further simplification of root over a square plus 1 plus I root a square minus 1. This is my capital B form, IB, plus 2 I root over a square minus 1. This is A and this is the B portion, which may be written as half, half root over a square plus 1 plus I root a square minus 1 whole square. Yes, I am able to express the given expression. We are working out on this particular problem. This is the problem. 1 plus I root over a to the power 4 minus 1. Of this expression, we are to find its square root. And I express this in 2IB form, that is a plus IB whole square, a required square root. Due to shortage of space, you may express it as plus minus 1 by root 2 into a square plus 1 plus I root a square minus 1. So therefore, each step should be clear. This is the given step. Why are you multiplying 2, sir? Your question could be simple as that. Because my 2IAB is not complete. It is incomplete. 2 is missing from here. So when I need to have 2 out here, I have to multiply 2 to numerator and denominator. This is how we proceed with the problem itself. This is how we proceed. This is my step. Then my next step is a square and this, because I am breaking up, and a square plus 1 minus a square minus minus becomes 2. So 1 plus 1 2 and a square gets cancelled. It is just you are rearranging the given expression to your form a plus ib. If I can express in this form, directly I can write its square root of this expression is this. Similarly, for the last problem, this a very important problem. Generally, students get confused. After completion of problem number 4, we move on to problem number 5. Find argument of 1 plus I root 3 into root 3 minus I of this particular complex number, and I find there is not one complex number, two complex numbers, 1 plus I root 3 is one complex number, and it is multiplied to root 3 minus 1. Now, I have one note to make, note 1. Argument of Z1 into Z2 is equal to argument Z1 plus argument Z2. And note 2, argument of Z1 by Z2, argument minus Z2. And my two complex numbers are in the product form. I have to use note 1. First and foremostly, individually, we would find their argument. 1 plus I root 3, argument of 1 plus I root 3, 1 is positive, root 3 is positive, therefore the complex number is in first quadrant. And if it is in first quadrant, we may write argument of this as tan inverse root 3 by 1, and its principal value is pi by 3. So first part, argument pi by 3. Argument of root 3 minus I is equal to root 3 is positive, root 3 is positive, and y portion is negative. This complex number is in the fourth quadrant in our Argand plane. If that be the case, then by our concept of argument, the value of the argument of this complex number is minus tan inverse 1 by root 3. Do not consider sign. I have told you in my part 4 of complex number. We are neglecting sign of x and y. We are only considering the positive value. So therefore, it is minus pi by 6. Therefore, argument of 1 plus I root 3 into root 3 minus I is equal to argument of 1 plus I root 3 plus argument of root 3 minus I, that is equal to pi by 3 minus pi by 6 is minus pi by 6 is the argument of this particular given complex number. So remember this particular note which says argument of Z1 into Z2. Do not multiply this. I have found out that students multiplying this. Please do not do that. As simple, let us make things simple. As things are made simple, it would be easy for you to remember. It would be easy for you to recollect in your examination, because examination are the ultimate. So therefore, let us keep things very simple. And then is the note 2, where if it is in the quotient form, if two complex numbers are given and they are in quotient form, Z1 by Z2, then our note 2 is applicable. This is as far as problem number 5 is concerned. I now move on to problem number 6. If omega is complex cube root of unity, show that x omega square plus y omega plus z omega y z omega squared. This is the problem based on complex cube root of unity, which we discussed in part 4 of complex number, that if a question is asked what is the cube root of unity, by our concept of complex number we would state that 1 omega omega square are the complex cube roots of unity. 1 is the real root, and omega square are the complex cube roots of unity. I gave you examples of 8 as well as 27 and a general term m, that what are the cube roots of 8? 2 omega square, 27 3 omega square, and then the general term where omega and omega square are the complex cube roots and the other is the real cube root. Here our problem says omega is cube root of unity. We discussed two properties also. First property, solution, that is, as omega is cube root of unity number 1, omega cube is 1, and number 2, 1 plus omega square is equal to 0. This is our given condition omega, and with the given condition I use properties. What are the properties of omega? Properties of omega is omega cube is equal to 1. I am proceeding very diligently so that you can follow this. At times I find students asking me that how do I know how to start a problem? Yes, that is a genuine case. That how do you start or proceed a problem? To start a problem, what is the given condition? Given condition is about the omega, and this is what I have to show. When omega is given, I have to add these two properties. These are the two properties which I am going to use to prove this particular left hand side is equal to right hand side. This is my problem. So these two conditions would be used. I would apply them in the left hand side and then I would prove my right hand result. So I start with left hand side. Left hand side is x omega square y omega z by x omega y plus z omega square. This is my left hand side, and I have to prove this whole thing is nothing but simply omega the right hand side by using these two given conditions. I straight away take omega common from my numerator. Sir, this is x omega, this is y, and this is z by omega. And the denominator remains same. Denominator is not changing. I have taken omega common from my numerator. And when I take omega common, left over is x omega plus y plus z by omega. That is omega x omega y. Let us multiply omega square to numerator and denominator. I am multiplying omega square to numerator and denominator. So this is z omega square, and the denominator is x omega y plus z omega square. This omega cube is equal to 1. I replace omega cube by 1. That is omega x omega plus y z omega square, because omega cube is 1. When omega cube is 1, so I can certainly replace this by 1. And after replacing, and my denominator is x omega y z omega square, I cancel out these two. Left over is omega, which is nothing but my RHS. Therefore, LHS is equal to RHS. There are several problems of this type in your exercise. Work out each of them. I just recap what I have done. This is my given problem, and omega is complex cube root of unity. When it is complex cube root of unity, two conditions are only available in hand. Omega cube is 1, and 1 plus omega square is equal to 0. So therefore, straight away I take omega common. Omega is taken out common from the numerator, and left over is my condition. I multiply omega square to numerator. Omega cube is 1, and I find that particular factor getting cancelled, left over with omega. This is problem number 6. I move on to problem number 7. Show that x y omega z omega square whole square plus x omega plus y omega square plus z whole square plus x omega square plus y plus z omega whole square is equal to 0. Now, I have chosen this particular problem. The reason is very simple. Here, our problem is in terms of x, y, and z. In different competitive exams, you may be given a problem that is x is replaced by say 99, y is replaced by 100, or z is replaced by 101. Somewhat huge quantities may be given. And generally students start squaring, and if you square 3 terms, it not only becomes huge, it becomes unsolvable. So in your examination, you may not be given x, y, z, you would be given a particular value of x, y, z, so that this problem you have to show it to 0. I would just finish it off within 2 minutes. So I start with left hand side, x plus y omega z omega square whole square, x omega plus y omega square plus z whole square, x omega square plus y plus z omega whole square. Keep this first term as it is without changing any term of it. I take omega common from this particular term. It becomes omega square x plus y omega z by omega whole square. And I take omega square common. Omega 4 x y by omega square plus z omega by omega square whole square, which is further written as x plus y omega plus z omega square plus omega square into x plus y omega plus z omega square. I have multiplied omega square to numerator and denominator is equal to 1 plus omega, because omega cube is 1. Since omega cube is 1, and the next part is x y omega plus z omega square whole square. Therefore, x y omega z omega square whole square into 1 plus omega square, which is equal to 0. So x plus y omega plus z omega square whole square into 0 is 0, which is equal to RHS proof. This is all for today as far as part 5 is concerned. I will be coming up with part 6 of complex number. Thank you very much.